Okay, get this. You've got a completely sealed box. Nothing in, nothing out. You pop it on a scale, and it starts getting heavier. Now that sounds totally impossible, right? It feels like it breaks one of the most basic laws of physics. But we're about to dive into a real experiment that seems to do exactly that.
And this is the number at the very heart of this mystery. 6 grams. That's how much extra weight a super sensitive scale picked up from a completely closed system. Now, that's not a lot. You could mail a letter with that. But in the world of physics, that's a massive, glaring anomaly that just screams for an explanation.
And that really is the central question, isn't it? How on earth is this possible? I mean, if you don't add any stuff to the box, how can it push down harder on the scale? To figure this out, we need to look deep inside the box, at a very, very special material with a secret that's literally hidden in its atoms.
The key to this entire puzzle, well, it lies in a single element: bismuth. You've probably seen it before, those beautiful, iridescent, staircase-like crystals. But let me tell you, its real magic is happening way down at the quantum level.
You see, bismuth is a real heavyweight on the periodic table, element number 83. Its nucleus is so massive, its positive charge is so strong, that it yanks its inner electrons into orbit at just insane speeds. We're talking a serious fraction of the speed of light. And whenever things move that fast, the wonderfully weird rules of Einstein's relativity start to kick in, even inside a single atom. All this leads to a powerful effect called spin-orbit coupling, or SOC for short. Now, think of an electron as a tiny spinning top, right? But it's also orbiting the nucleus. Well, in a heavy atom like bismuth, these two movements, the spin and the orbit, they get intensely tangled up with each other. And this powerful connection creates incredibly strong internal magnetic fields, or what physicists call magnetic moments.
So, what's the big deal with these magnetic moments in bismuth? Well, they aren't just random. The actual crystal structure of the metal itself acts like a little roadmap, forcing most of these moments to point in a preferred direction. This built-in alignment, that's the key. It creates some pretty wild effects and gives us something we can actually get a handle on and control.
Honestly, the best way to wrap your head around this is to imagine the bismuth crystal is just jam-packed with trillions upon trillions of microscopic, super powerful gyroscopes. Every single one is fixed right into the atomic structure. And just like a regular gyroscope, once you get them spinning, they really don't want to change their direction.
So we've got these tiny, powerful gyroscopes. The problem is, they're all just kind of doing their own thing, pointing in random directions and canceling each other out. So the next piece of the puzzle is figuring out how to wake them all up and get them to spin together in one big, synchronized dance.
So how do you do that? Well, the experiment has 3 key steps. First, you need energy. They get this from a slow chemical reaction happening right on the bismuth surface, which basically feeds vibrations into the crystal. Second, you need coherence. A massive 10,000-volt electric field forces all those tiny random gyroscopes to just snap into alignment, all pointing the same way. And finally, here's the magic step: synchronization. That electric field is pulsed at a very precise frequency, which makes all the gyroscopes start to wobble or precess in perfect, coordinated unison.
Now, before we get to the big reveal, we have to talk about one of the most fundamental rules of the universe. It's a law that just can't be broken, and in fact, it's the very reason this whole thing happens in the first place.
And that principle is the conservation of angular momentum. In plain English, it just means that for any closed system, the total amount of spin has to stay the same. You can't just create rotation out of nothing.
So here's the crucial point. If you can get trillions of tiny internal gyroscopes to suddenly start spinning together in a coordinated way, you've just created a massive amount of internal spin, or angular momentum. To keep the total momentum of the box at 0, which the law says it must, the box itself has to react. It has to generate an equal and opposite motion or force to balance the books.
And with that final piece of the puzzle, we can finally understand what in the world is happening on that scale. We've got the energy, we have the alignment, and we have a law of physics that absolutely demands balance.
So when all those trillions of microscopic gyroscopes are forced to spin in perfect unison, they generate a collective, unified momentum. And to conserve the total momentum of the whole closed system, the entire bismuth structure produces an equal and opposite force. In this particular experiment, that force is directed straight down, a real macroscopic push against the scale.
At the very beginning of the experiment, as the system is just starting to sync up, the effect is small.
The scale registers an increase of about 1.5 grams. The gyroscopes are starting their coordinated dance, but they're not all quite in step just yet.
But as the reaction continues and more of these SOC moments are pulled into perfect synchronization, the effect gets stronger. The downward push gets more intense until it hits that peak of 6 grams. That's the moment of maximum coherence, when all the internal gyroscopes are working together to produce the biggest possible counterforce.
So what happens when you turn the system off? It's simple, really. While it's running, the scale is measuring the box's actual physical weight plus that extra downward push. But the second you kill that electric field, that beautiful synchronization is lost. The gyroscopes all fall back into their random states, the thrust completely vanishes, and the scale reading snaps right back to the box's true weight.
And this is the most important takeaway from all of this. The mass of the box never, ever changed. Not a single atom was added or taken away. What was created was a temporary directional force, generated by messing with the quantum relativistic properties of the material inside. The box didn't actually get heavier. It just pushed down a whole lot harder for a little while.
And this leaves us with a really fascinating final thought. Look, this was a tiny experiment on a lab bench with a very small effect, but it proved a principle. You can generate a net force from within a closed system without shooting anything out the back. Now, if this effect can be understood, if it can be scaled up and controlled, what could that mean for the future of travel, both here on Earth and maybe, just maybe, out in space? It's a question that really pushes the boundaries of what we all think is possible.